Hello, everyone, and welcome back. So, today we're going to be talking about a really exciting kind of further topic in everything we've kind of seen this quarter, which is really talking about kind of what's the limits of what we compute efficiently. And so, you may or may not have heard of this P versus NP thing before. It does sometimes get picked up in articles and stuff like that because it is a big open question in computer science and mathematics that hasn't been answered for a very long time. And so in this kind of series of videos, I'm going to introduce what this problem is, what is it trying to ask, and what we currently think about the world in terms of what the answer might be, even though no one has proved it quite yet. Before doing any of this stuff, I want to kind of do a little bit of a recap of some things we've seen before and some new things, like introducing some new things to kind of tie into the story of P versus NP better. So I'm going to start actually with a brand new problem that we've never seen before. What I call this, and since I want to quickly mention, since this is an optional video, I don't have any concrete learning objectives for you. I just want you to sit back, enjoy this, and hopefully learn something cool. So I want to start with this thing called 2SAT, which is a problem where you have a Boolean formula, like an if statement, and it's in the form of like A or B, and not A or B, and you have a bunch of these ands of ors. And the question for 2SAT is you have this formula where all of these kind of individual parts use two terms. The question is there a setting of these variables that make this formula true? We call this a satisfiability problem because we're asking, can you satisfy this formula, make it true by a certain setting of the input variables? Now, there are more general versions of the satisfiability problem that we'll talk about a little bit later. But 2SAT is specifically like formulas of this form. So it's kind of a limited set of formulas, but the question is, can you look at this formula and come up with a setting of A and B? Now, I'm not going to explain to you how you solve this problem. What I'm going to tell you, or I'm going to claim, is that there's an efficient algorithm to solve 2SAT. You give it this input string, or give it this equation, this Boolean formula, and it will output in polynomial time. I'm not going to tell you exactly what its runtime is, but you could imagine it's something like n squared or n cubed, depending on what you define n as. That's not an exact answer. I'm kind of making that up. But there is an efficient algorithm. Now, the reason I'm not telling you its runtime and the reason I'm not showing you the algorithm is because I want us to get used to treating algorithms as a black box. As a routine, you can call and it will give you an answer. You don't necessarily need to know how it works or how efficient it is. But we'll talk about today the importance of a polynomial time algorithm. One that has some polynomial runtime, n squared, n cubed, n to the fourth, but is definitely not exponential. So I will tell you right now that this 2SAT problem is solvable in an efficient way in some polynomial time algorithm. Okay, so that's kind of the new problem. Now I want to go back to, I want to go switch gears just a little bit more. I want to talk about a slightly different problem. So this one I want to talk about is a graph, a problem that, coloring a graph, a problem that doesn't seem very similar at all, but we'll actually see as some kind of inherent link between them. So the problem of coloring graphs is a general problem. You have a graph with nodes and edges, and you want to assign each node a color such that no two nodes that share an edge have the same color. So for example, in this 2 coloring, I need to give each node here a color. I believe I chose either blue or orange. So for example, you might start by making this node blue, and then you make all of its neighbors orange because you can't let a neighbor be the same color as it. And then you could make those ones neighbors blue. So you can kind of alternate which color you use. So this graph is 2 colorable, meaning you can assign 2 colors to it, or to all of the vertices, such that no 2 vertices that share an edge have the same color. Now, you might be wondering, is it always possible to 2-color a graph? And the answer is no. So there are some graphs that aren't 2 colorable. For example, this one. So for example, if I color this one blue, and then its neighbor's orange, and then their neighbor's blue, well, now we have a conflict because C and D are neighbors of each other, and they're both blue. So not all graphs are 2 colorable. And so the 2 coloring question is, given a graph, can you 2 color it? Or a similar way of asking that question is, given a graph, what is the 2 coloring if there's one that is? if there one that is well, if there is one that exists. So they don't always exist. So my question is, let's try to come up with an algorithm that colors a graph. Now, why might you care about coloring graphs? Well, sometimes we talked about graphs representing lots and lots of different things. And sometimes you have some notion of a graph representing kind of conflicts. So for example, you have a series of vertices, and edges mean, an edge in your context might mean that these two vertices don't belong in the same set. Like maybe they're enemies or something like that. And one way of framing a two-coloring question is, can you separate all the vertices into two groups such that you never put enemies together or something like that? So lots and lots of applications of this two-coloring. So we could come up with a new algorithm to solve this. And I'd argue it's actually not too complex. All you have to do is just take BFS and modify it a bit. That's actually a really interesting exercise. I'll leave that for you. But what I'm going to have us talk about today is solving this with a reduction. So we're going to reduce two-coloring to something that doesn't look anything like this, like coloring a graph at all, this two-sat problem. And so first, let's go and recap. What is this idea of a reduction? Remember, a reduction is trying to solve a problem P with another problem Q's algorithm, but using it as kind of a black box. So the idea is you change the input to P to become an input for Q, and then you run the algorithm for problem Q as is without modification. And then when you get the output there, you need to somehow transform it back into your original problem. So remember, reductions are a general problem-solving technique to kind of not reinvent the wheel each time. And so if you're able to spot this core similarity between problems, you can reduce your problem to a problem you have an algorithm for and just call that. So what I'm going to have us do today is reduce two-coloring to two-sat. So in order to do a reduction, we need those two steps. Turn a graph for two-coloring into an instance of two-sat. I'll fix that typo in my slides. It's supposed to say two-sat. Then we run the two-sat algorithm, which I didn't describe to you, but I'm telling you it exists. And then we take the answer from that two-sat and a setting of those variables that make the whole formula true, and somehow to turn that back into a graph coloring. So here's the key idea behind this reduction. A specific technique to do this particular reduction is we're going to use logical formulas to encode colors. So we're going to have a variable for each vertex saying like, is that vertex red or orange or whatever color you like? And then we just need to make up formulas such that all of its neighbors don't have the same color. So you might have some formula like either V1 or V2 is red, and it's not the case that they're both red. That makes sure that they both are kind of using different colors and they don't have the same color. So we can, just for two vertices, we can come up with this formula. And so the reduction is just coming up with these formulas for the entire graph. And so this is what this will look like. We start with our graph, and we transform the input in the way I just described. So for each edge, you make a formula saying that one side of the edge is red or the other side is red, and they're both not red. And so you make this really, really complex formula for the graph. Then we just throw this formula at our two-sat algorithm. And it's going to run that efficient algorithm that will determine if it's satisfiable or not. And it will output all the settings for true and false. And since we made each of these variables like is A1 or is A red, we can read off these answers and turn it into a colored graph as the output for our original problem. And so we can color them as such. This is the huge power of reductions. We didn't have to come up with a brand new algorithm. We really just had to come up with a way of transforming a graph into something we already knew how to solve. And with the disclaimer that we didn't quite know how to solve that two-sat problem, but you don't need to in order to do a reduction. All you need to know is that there is an algorithm you can call to solve that problem, hopefully efficiently. Now, you might be wondering, okay, Hunter, why are we talking about Boolean formulas and graph coloring? What does this have to do with the a currently unsolved problem in computer science? What is the deal here? Well, first reason was I wanted to remind us that reductions are powerful tools for solving problems, especially because the example I showed you last time actually was kind of a failed reduction. But I also want to remind you of reductions because they're going to be a powerful theoretical tool in proving relationships between problems, namely, is one problem easier or harder than another in some sense? Now, for the rest of the videos today, I want to preview kind of what this P versus NP problem is going to try to get at, and then I'll explain what those terms mean. So if you just take everything we just talked about, 2sat and 2 coloring, and you just change those 2's to a 3, so 3sat would be these Boolean formulas with 3 terms per clause, and 3 coloring a graph using 3 colors. If you just make that very simple modification, it turns out that there is no known efficient algorithm to solve it. I told you that there's an efficient algorithm for 2sat. People have been working on this problem for well over 50 years, and no one has found an efficient algorithm for 3sat. So even though our reduction might be the same, that algorithm to solve 3sat would not necessarily be efficient. And so the whole runtime of that, our 3 coloring, is also inefficient. So another kind of weird thing that comes from this fact that 3sat doesn't have any well-known or any known efficient solutions, is also kind of unintuitively, if you came up with an efficient algorithm for 3sat, just suppose you're able to come up with one, then you would get, in some sense, for free, solutions to a huge set of currently intractable problems that we currently don't have efficient algorithms for. These problems include, but are not limited to, the traveling salesperson problem that we talked about on Friday. Also, folding proteins to make new drugs that could save people's lives. That turns out to, in some sense, be somewhat similar, if you squint in a really weird way, to be the same as the 3sat problem. And even weirder, scheduling UW classes to somehow maximize student demand for courses. All of these problems somehow have the same kind of core hardness to them, but we don't know why they're hard. And that's kind of the fundamental question of this P versus NP thing that we're going to introduce in the remaining videos, is what makes a problem hard, or what makes it easy, and why, and how can we relate these problems or these qualities together? So that's kind of our overarching context for today's video. So hopefully you watch the next one and the one after that, where we introduce kind of why these things are true about 3sat in particular, and what we currently don't.